Okay, for the test tomorrow over the stuff we've covered in Chapter 9 plus a little extra stuff I've added in there. The first few sections were on antiderivatives. So definitely make sure you know how to find antiderivatives, all the antiderivative rules, which are basically just your derivative rules backwards. More so on the trig functions. If you can remember your trig derivatives, then just go with the answer, and the antiderivative of the answer is what you were taking the derivative of, if that makes any sense whatsoever. And of course the power rule. The tricky part with those, a lot of you have been asking with the fractions, like Leo was just doing over there. One term in the denominator, you got to separate out into the numerator over the denominator plus the second term and third term and so forth. Simplify it algebraically, get it in the form, you can use your power rule and then do the antiderivatives. Now, at that point, we hadn't done any other integrals. It was all antiderivatives. Don't forget, we have something like that. The answer to this would be what?
X squared over 1 plus c plus u.
Okay. Do not forget that plus c.
Only if it doesn't have a value, right?
Correct. If there's no numbers on the integral sign, then that's the antiderivative. That means the plus c is part of the answer. Because in that case, the answer is what function has x as the derivative. Well, it could be x squared over 2 plus 1, or minus 3, or something like that, or maybe just plus 0. But you leave the plus c off of there, and you're giving 1 out of an infinite number of possibilities. Okay, so make sure you get that plus c on there. Now, if you're finding a definite integral, do not put the plus c on there, because we're finding a particular value, and we're not going to be able to add any number to the end of that. So, okay, so antiderivatives, lots of formulas there. Probably the trickiest part, finding antiderivatives through substitution. Okay, make sure you know how to do that. And then, of course, this last couple worksheets we've been doing antiderivatives and then plugging in our definite integral limits to calculate that definite integral. So we've kind of come full circle. The largest part of finding the definite integral is finding the antiderivative. But then we're not quite done. Plug in your values and calculate. But antiderivatives are important. We'll have several. Okay, so with the approximating, I'll limit it to just 4 rectangles, so it's not a page long. Doesn't take you 30 minutes to do one problem, but probably 4 using left endpoint and or right endpoint, one or the other, or maybe both. So be able to do that. And then, of course, this led us up to finding the definite integral value using the definition. And in most problems, I just say, find it, evaluate it, I don't care how you do it. But in this particular problem, it will say, use the definition of the definite integral to evaluate, and then you'll have the problem. Now there will only be one of those. I'm not going to put 3 or 4 on there. Again, I want you to be able to finish tomorrow. So, but with that, let's see. I think I also put something like the limit definition or find the limit, something like that. But you will definitely know which one is using the long way rather than the short way. Any of the other problems where I just say evaluate, you can use the shortcut. Now, in these problems, we had to know the summation formulas. The only summation formulas I will require are the sum of a constant and the sum of I. I'm not going to have you do I squared or I cubed. Don't worry about remembering those. I have a hard time remembering those. So, but sum of a constant would be what?
N times N.
Okay, the constant times n, and the sum of I.
It's N times N plus 1 divided by 2.
Okay. So as long as you know those two, you'll be fine with the definition. Okay. The biggest part of that is partitioning your interval. Make sure you start at A. It may be 0, which would make things easier, but it may be -1, it may be 2. You got to keep that in mind as you're setting it up. And then it's your choice what your sampling number is. My suggestion, use the right endpoint, use x of I, and plug that into the function. So, any particular questions on that? Okay, a lot of detail on that one, but kind of
The definition of the definite integral to evaluate the definition of the integral. Which one is that one?
to evaluate the definite integral. That was,
Okay.
yeah,
Okay.
with the I and, okay. So let's see. From there, we looked at the fundamental theorem of calculus, and you know it's a key part when it says fundamental theorem. This is it. This is the reason we study calculus and can pull it all together. But the fundamental theorem, now, he kind of presented it in 2 ways, and there might be some problems with both ways. The first one was basically if f of x was defined something like this. I'll just go make it easy. So if your function is defined in the form of a definite integral, then the derivative of that would turn into what?
X squared plus B.
Okay, it's just that part there in terms of x. But so the idea is this is kind of an operation that gets undone by this operation. Take the derivative of an antiderivative. Well, this really isn't an antiderivative, but kind of that. Take the derivative of a definite integral and they cancel each other out and you're left with just this part. Yeah.
So on the ones that don't exist, is that just you knowing that, like, over that interval?
Yeah, the interval is important. If we have a restriction on the domain of the function in here, like if it would be 1 over t from 0 to x, well, 1 over t from 0 to x would be a problem at 0. That one would be does not exist because the function doesn't exist at 0. So,
Do we have to write the because the function doesn't exist at 0? Or?
nah, just does not exist would be sufficient. Okay. So now this side of the fundamental theorem we do not use nearly like we use the other one. Of course, the other one, if you have 0 to, say, 3 of x squared plus 1 dx, use the fundamental theorem to evaluate, or if I just put evaluate, you can guarantee there's going to be a few of evaluate definite integrals.
Are you gonna tell us that to do the fundamental theorem? Like, are you
No, I'll just say evaluate. You do it whatever way you want, which is probably the fundamental theorem. But calculate your antiderivative of this, and then go from 0 to 3, f of b minus f of a, minus, make sure you get the parentheses in there. Of course, if it's 0, most of the time, not always, but most of the time that part's going to be 0. But double check every time. So, let's see, we'd have 9 plus 3. That definite integral value is 12.
And that's still the fundamental.
Yeah, that's the fundamental theorem going kind of the other direction. This top part was starting with the definite integral, find the derivative. The derivative is the inverse operation of the definite integral. And this is saying, okay, here's your derivative. This is your antiderivative. We calculate that first and then evaluate it at the endpoints. So, yeah, it's kind of hard to explain the relationship there. Much easier just to work through it. But the theory behind it, it's still both parts of the fundamental theorem. Thankfully, we use this one a whole lot more than that first one. Okay. So, be several evaluate a definite integral. Also, might be some find the area under some function and above the x-axis, or maybe it will be below or under y equals some function over the interval from like 1 to 3, or in this case from 0 to 3. This 12 represents the area under this curve from 0 to 3. But there might be a problem where the interval, the x-interval, is not given. When it says above the x-axis, that we've got to do some algebra to find where the integral limits are. And that would be where this turns out to be 0. So maybe it's a parabola. Goes, I think one of the problems on the worksheet was a parabola that might have went like this, and find the area under. Well, first thing we'd have to do is find where the function equals 0. And in this case, maybe a -1 and a 3. But that'll depend on the equation. Probably solving an equation. Probably a quadratic. I mean, at this point, we're not going to get too out there. That'll be next unit. Well, it's not that scary, but okay. So, let's see. Find the area under. Trying to think. Then the last thing we looked at. Then before we look at that, another problem of, well, not necessarily area, but given the function as a graph, evaluate the definite integral, say from 1 to 5 of f of x. Now, in that case, y equals f of x will need to be a nice set of straight lines so we can figure area under curve. And maybe, let's see, from 1, maybe it'll be something like this, 2, 3, 4, 5. That's probably not a good setup there, but find the area above the x-axis. That part would be represented by a positive value for the definite integral, and then anything below the x-axis, that area, we'd calculate the area, but the definite integral would be a negative value for that. So, okay. And like I said, it'll be rectangles and triangles that you can separate those into. Okay, and now the very last part, what we talked about yesterday, was the approximate a definite integral using either the trapezoidal method or I guess I should say and or Simpson's rule.
You want us to use both or just one?
It may be two different problems, one being the trapezoid, one being Simpson's, but I won't throw that all into one problem. But trapezoid, and these are formulas you will need to know. So trapezoid formula is what?
1/2.
B minus A over N.
Okay, b minus a over n.
F of x 0.
And then no, plus 2.
Okay, 2.
And then plus just normal.
Okay, I guess we probably should do
Should be
more than
also-
that. Oh.
This is the last one.
And then the last one is what changes.
The last one.
Yeah, the last one goes back to 1. And like normal, running out of room. Always write bigger than I think I'm going to. So that one's pretty straightforward. We have just the 1 first and last, and then everything else times 2.
What's the last one mean? Not the very last one, but
This one?
Yeah.
The second to the last one. X sub n minus 1. If n is 4, then n minus 1 would be 3. So just a fancy notation of saying the one before the last one.
Something to confuse me.
Yeah, that formal mathematical notation. Now, Simpson's rule, a little bit more to remember, but let's see, first of all, it's what?
1/3.
Okay, that one's 1/3.
B minus A divided by N.
Okay. So,
First normal.
and notice both of these are b minus a over n, which is just your delta x. So the part out front to remember, trapezoid is 1/2, where Simpson's rule is 1/3. Okay. And then the pattern on the inside is a little different. First one is still 1. Then we go what?
Plus 4.
Okay, 4 for the f times f of x of 1 plus 2
And then
f of x
so
of 2,
it repeats the pattern.
4, 2, 4, 2, and so on let's see.
I have a question.
I'll throw Francisco off here a little bit. There we go.
So it always
Does that make
gonna-
sense?
Is always,
Now, well, good.
is it always gonna end up with a 4 or with?
Yeah, the second to the last one was always going to be a 4.
So even if there was going to be a 2 with the original pattern, you still change it to a 4.
It always must be a 4 at the end, at the second to the end, because in this method you have to use an even number of partitions. N must equal an even number, where the trapezoid n could be either even or odd, but Simpson's rule has to be even, so the second to the last one always will be 4.
But what if it's not even?
Then you can't use Simpson's rule. If it's not an even partition, then you can't use Simpson's rule.
Wait, can you explain
That's
that?
all.
How do you get an even number?
Normally, if you're wanting to find the value of this, you get to choose. So you would have to choose an even number for n, for Simpson's rule.
Like n cannot be 5
Right.
or 3.
For Simpson's rule, you would never use n equal 3 or n equal 5. Always
Any
must be.
odd number. Okay.
Right. And that's your choice. I mean, in general, I mean, I will tell you the details of that, but out in the real world, if you have to calculate something like this and don't have an antiderivative exact value to use, then you would be choosing, well, let's let n equal 10 or n equal 20, depending on how accurate you need and how much work you want to do. But you would never be able to choose n equal 5 or 15 or anything like that. Okay? Okay. So like normal, 20 problems. Many of them will be finding antiderivatives or finding definite integrals and using the shortcuts. But a few of these other detailed problems scattered in. Find area, find your approximate using either left or right endpoints or trapezoid rule or Simpson's rule, and definitely one of those that's use the definition of the definite integral. I think I put limit process, so be calculating the limit. Any particular problems, any questions? Yep.
I kind of want to go over the definition. Just like
Okay, we can do the definition. Let's see, let's go.
Hopefully we have about half an hour or something.
Does it matter how the way you start on those?
Well, this will be given. Okay. And as I said, I'm not going to give you where you'd have the sum of I squared or sum of I cubed. So, which basically will be a linear equation as we're integrating the function. But, okay, the problem will say use the definition of the definite integral to find this. What we need to do, well, several little things to start off with. Probably the main thing, first thing, find delta x. That's going to be what?
Oh, 4 over n.
Okay, right. B minus a over n, so 4 over n. Yeah, that's a 4. Okay. Then, what I would do, we need to figure out what our x sub I is. Well, this time we're starting at 1, so, and technically that would be your x sub 0. So x sub 1 would be represented by what?
1 plus
4 over
Okay. And a little more general, that's going to be a plus 1 delta x sub 2,
A plus 2 delta x.
and you can kind of see that
Your I is
this would be delta x, from 1 to 2 would be another delta x, so kind of following that pattern. So in particular, we'd have 1 plus 2 times 4 over n. Now you could go ahead and multiply and say 8 over n, but it's going to be easier if you just leave it in this form. So when you get your pattern, okay, so it's probably enough to see what's happening. X sub I is going to be what?
1 plus I times 4. Can we just, do we have to write the other stuff, or can we just write that?
No. If you recognize it right away.
Okay.
1 plus 4I.
Okay. Now that's the x value of each subinterval, the right endpoint technically of each subinterval. But what we need in the summation is f of x. So plug this into the function. So 3x plus 1. And let's see, are we ready to put it in the limit form? Now, technically, the limit is as the mesh approaches 0. Well, because we have chosen this to represent all of the partitions, n approaches infinity will make the mesh approach 0. So we can go directly to that form of the limit. And then that's the summation of f of x sub I, which, let's see, we could probably simplify this a little bit before we plug it into our limit. Multiply the 3 through, and 3 times I times 4 over n, probably best to go this way. And then plus the 1, don't forget about the 1. So f of x sub I, 3 plus 1, we could write that part as 4. And then we have the 12 over n times the I. So whatever order you want to write that in. Doesn't really matter with the plus. And then don't forget times your delta x. Okay. Questions so far? So, let's see. Let's go ahead and... At this point, lots and lots of algebra. We could rearrange stuff lots of different ways. I like to go ahead and get that out in front of our summation. So we'd have the summation of 12 over n I plus the summation of 4. So we'd have the 4 over n times both parts, then the 12 over n times the summation of I. And at this point, summation of I, when we go directly to the formula, would be what?
N times n plus 1 over 2.
And then the 4 formula for that would be what?
4n.
Okay. And now lots of algebra. a little bit simpler than some of them we did on the worksheet. But this first part, n divided by n, we can get rid of that. We'd have 12 divided by 2 would be 6. So that part right there, we still have the n plus 1. So 6n plus 6 plus the 4n. Now that's still all times 4 over n. And let's see, we'd have 10n. So our inside would be the 10n plus 6, and we still need to multiply that by 4 over n. So let's see, we'd have 40 plus 24 over n. And now as we apply n approaching infinity, this last term goes to 0. Limit of a constant is that constant, so our definite integral will be 40. Now, of course, we could check that, make sure we get the right number, but that's how we do it with the definition. Okay? Questions? Just lots and lots of little details on that one, and try not to forget one. That's where little mistakes are made. Other questions? So approximating this, of course this one we could find the exact value, but we want to show how we can approximate using the left and right endpoints, and as I said, we'll keep it just to 4 rectangles so you don't have a ton of work to do on these. What we have to do first, like the definition, find your delta x, and in this case that's going to be what? Okay, we go b minus a minus the negative 1, so we'd have 2 over n, which is 4. So delta x is going to be 1/2. Now sometimes we've worked a lot of them with 1/2, but it's not always going to be 1/2. Maybe it'll be 1/4, maybe it'll be even 1. Hopefully it'll be 1. That'll make life a lot easier, but probably not. But anyway, 1/2. Now, the endpoints, we need to figure out the endpoints of each subinterval, and we start with -1. We'll end at 1, so with 4 of them, we'll need to figure out what these 3 inner endpoints are. Well, this one, -1 plus, well, there's our delta x again, -1 plus 1/2 would be -1/2. Then the next one, well, that one's going to be 0, and then 1/2. Now, we'll be able to use these x values in both parts. We don't need all 5 of the x values in both parts, but we do need 4 of them. Okay. Left endpoints. Now remember, we're looking at area of a rectangle. The width of that rectangle would be the delta x. The length of the rectangle is your function value. So with the left endpoints, we would have f of -1 times our delta x plus f of -1/2 times delta x, and I'm showing a lot more work than you'll have to do, but just to see where it comes from. Now what I would do, instead of multiplying each individual term by delta x, factor the delta x out, Just make sure and remember to multiply by the 1/2 once you're done. That's the most common easy mistake to make, is forget about the delta x. But
So you can put that in sigma notation.
yeah, but really what I would do is more put these 4 inside and then have your times delta x on the outside. So f of -1, well, x cubed plus 1, that would actually turn out to be 0. Okay. Then f of -1/2, -1/2 cubed would be -1/8 plus 1, 7/8. Now, you don't necessarily need to do fractions, but I'm not sure if I say round to the nearest whatever, but probably if I don't say, maybe go 2 to 4 decimal places, whatever's kind of reasonable on these. But there's f of -1/2, f of 0, oh, that's a nice one. And then finally your 4th rectangle, f of 1/2, and that would be 9/8. So, keeping them in fractions, it turns out not to be all that bad. 7/8 plus 9/8 is 16/8, or 2. 2 plus 1 would be 3. And then 3 times the 1/2, 3/2, or 1.5. That would be your left endpoint. Right endpoint, the only thing that would change, we would not start with f of -1, but we would start with f of -1/2, because that's the right endpoint of the first subinterval.
Okay,
So,
I got it.
yeah, and I'll let you fill in there. We've done all the calculations except this very last one. So a lot of the same numbers are used, but and again, like I said, don't forget times all of that by your delta x. That's the most common. That's what I always forget to do, and then I look at the answer and go, why is that not the same as mine? But okay? Any other questions?